Okay, lesson 6.8, applications of arithmetic and geometric patterns. I've taken the time to actually write things out first this time, so it should go a little bit faster, hopefully. Our first question is, if we deposit $1,000 at 4% compounded quarterly, how much money is in the account after 10 years? So in this kind of question, we have to know, first of all, how do we find compound interest? So we have this compounded interest, and the compound interest formula is one you've probably seen before. I think we did it last year in class. And it says the following. If I want to know how much money is in the account, then I need to know what I started with. That's called our principal. 1 plus r over n raised to the nt. So this is our formula. Each one of these letters has a purpose. A is the account balance. P is the starting amount. R is the rate of interest. Okay, make sure we make that into a decimal. So in this case, 4% would be 0.04. N is the number of times we compound the money. And T is time measured in years. Okay, so that's what we have. So basically now we just got to fill in what we know. We want to know how much money there is after 10 years. That's A. We know we started with $1,000. We know our interest rate was 0.04. Quarterly means how many quarters are in a year? There are 4 quarters in a year. N times T would be 4 times 10. At this point, you're just basically putting this into the calculator. If you want to simplify it just a little bit first, we got 1,000. This is going to become 1.01 when you work that inside out there to the 40th power. And that means after 10 years, your account will now have $1,488.86. So the compound interest formula, I don't believe is given in the booklet. I'm not sure if it actually shows up on the IB questions or not. If it does, we'll figure that out as we get closer. All right, next question says this. The population of a town increases by 2% each year. If the population in 1980 is 12,500 people, what is the population in the year 2020? So this is a population growth. Okay. We could also refer to this as exponential growth. And I'll have to check and see what the formula sheet has. And I think this might be on the formula sheet also. But to find population or exponential growth, our new amount is going to equal our starting amount, 1 plus r raised to the n. N is just going to be time, so we could actually use t there if we want to, or we can use n. Okay, but this is time. And time can be measured in any kind of way. In this case, it's going to be years, because we're going from the year 1980 to the year 2020. So n is going to equal 40. There's 40 years that pass in that time. The rate is going to be 0.02. We started out with 12,500 people. And now we just got to put the information in. So we got y equals 12,500. 1 plus 0.02 is going to be 1.02 raised to the 40th power. Putting that into a calculator, we get y is equal to 27,600 people. Okay. So after 40 years, the population has more than doubled. Okay, next question. If I have an arithmetic sequence, so here's my arithmetic sequence. Now, this is simplified already. Right? This did start out initially as u sub n equals d parentheses n minus 1 plus u sub 1. But it was simplified. I have a geometric sequence. V sub n equals. And the only reason they use v is because they already use u for the arithmetic sequence. So just to make a distinction, it's kind of like f of x and g of x. We want to find the least number of terms, so find n is what we're really being asked to find. Find n such that v of n is greater than u of n. So, several ways you can do this. You can set these two things equal to each other. And if you do that, then you would have to basically, at that point, start finding a way to solve for n. But one of the problems that you run into there is that you see that n is in two places, in a normal position and in an exponent position. So if I want to find out where two equations are equal, we can actually go back to using the graphing calculator. So a lot of these questions are going to be graphing calculator type questions, and you're able to basically at that point use the y equals menu. Okay, so we want to do this. When is 0.3 times 1.2 to the n minus 1 equal to 12n minus 7. So we're going to look at it like this for a second. And then what we can do is we're going to take this left side of the equal sign. We're going to call this y1. We're going to look at the right side of the equal sign. We're going to call this y2. And we're going to put it into the calculator. And we're going to graph it and find where the intersection is. So let's see if this is going to work for us. So we're going to go to y equals, clear out our equations, and we're going to put in our y1, which is 0.3, parentheses, 1.2, parentheses, raised to the x minus 1. Come down to y2, it's going to be 12x minus 7, 12x minus 7. And we have to pick a good window. Now, I already know what the window is going to be. I'll just put it in there, 0 to 100 on the x-axis, and we'll go by tens, and we'll do 0 to 1,000 on the y-axis, and we'll go by hundreds, and we're going to graph it. So there's the first graph, here's the second one. Right? And if you look at this, this is going to be our y1, which was the geometric one. Okay? This is v sub n. And we also have our y2, which is u sub n. And right here where they intersect is when v sub n eventually now becomes greater than u sub n. So we got to find where this point is. And we know how to do that on a graphing calculator. So we're going to go into the calculator, do second, trace, calculate. We're going to calculate the intersection, 5. We just hit enter 3 times. 1, 2, 3. And down here it tells us that it intersects intersect at 41.6. Okay, so if I were to just take a screenshot of this, let's see if this will work. And we're going to put that screenshot right in here. Let's see. A little out of practice. I got to figure out how to do this part again. That doesn't do it. All right, hold on a second. Let's see. One last try, and then I'll just ignore it for now. There we go. All right, cool. Shrink it down a little bit. There we go. All right, so now we have this, and at this point, I can see that the graphs intersect at 41.6. So we're going to say this. Since x equals 41.6, n would have to equal 42. Because we have to go a little bit further than that point in order for a whole number to be the right answer. So n would have to be 42 in this case. Okay, so if we look at the original question said find the least number of terms such that the v sub n is greater than the u sub n. So it has to be at least 42 terms before that gets there, because we can't do part of a term. All right, so let's just save this for a minute. Lose anything, and we are on the next example. Geometric sequence, the first term is 6, and the common ratio is 1.5, and arithmetic sequence, the first term is 75, and the common difference is 10. Yep, that's not right. The common difference is 100. When will the number of terms, so we're trying to find the number of terms again. The sum of the geometric sequence be greater than the sum of the arithmetic sequence. Okay? So we got that. And let's just move this down a little bit. Okay. There we go. Okay, so think about what we know. We know the geometric sequence is given to us S sub n. The sum of n terms would be 6. 6 is the first term, times 1.5 to the n minus 1 over 1.5 minus 1. We're going to make this y1 in the calculator. We also know the arithmetic sequence, the sum is going to be And number 2. Now just pull these formulas from what we've been doing the last few sections. 2 times the first term, 75, plus n minus 1 times the common difference of 100. We're going to set that equal to y2. Now, to save a little time, because I showed it in the last example, I'm going to set up my window based on what I find is going to be necessary. And for my window, on the x-axis, we're going to go from 0 to 30. Okay, we can go by 5s. And on the y-axis, I found that I had to get pretty far, 20,000, 0 to 20,000. And so I'm going to go by 1,000. I do the same thing that I normally do. I just put that into the calculator. And after I calculated it by finding the graph, do the second calc intersect again. Oops. Hold on 1 second. So I go back to my calculator, I do second trace intersect. And I find out that x is about 17.8. I'm not going to do all the calculator thing on this one again. So 18 terms before the geometric sequence is greater than the arithmetic. Okay, last example. So we got 2 species of spiders. Species A starts with a population of 12,000, increasing at 1.25% per month. This one is geometric. Species B starts out as 50,000 and decreases by 175 spiders per month. So this is arithmetic. It goes down by a common difference. When will the population of species A be greater than species B? So there's our question that we're trying to figure out. So we're going to do the same thing again, y1, y2. So for species A, we're going to have the following. y1 equals our starting amount, 12,000. Our rate, 1 plus 0.0125. So it's going up by 1.25% to the x. And for species B, we're going to start out with y2 equals our starting amount, 50,000, and it's going to go down by 175 per month. I figure out what my window needs to be. So in this case, I found a window. A good window would be 0 to 100 on the x-axis. By 10. And on the y-axis, I had to get all the way to 50,000 because that was the most I had. So 0 to 50,000. And just to make it easy, we just went by 5,000. Second trace calculate again. Number 5 for intersect. Oops. And I found that x equals 86.03. So that means it took about approximately 86 months. Okay. And that is that.